Hi folks, Mr. Long here. Now we're going to start doing some calculations on vectors and some very fundamental ways that we measure vectors. Okay, very fundamental ways. So here we go. So part A, again you have this handout, so hopefully you've printed it out or you're working on it online and filling it out as you go. Remember that a geometric vector is just a picture. A Cartesian vector has this form, right? And a Cartesian vector is also called an algebraic vector. And what it means is delta x is how much does x change by when I go from A to B. Delta y is how much does y change by when I go from A to B. Right? It's a linear translation. So, and I wrote down the points from up above there, A and B. Those are the pairs. So it's a translation from A to B. So you put an object at A, and then you're going to move it to B. Okay, you are taking the fastest route, which is a straight line. Okay, that's why they call it a linear translation. A vector is a linear translation, and it's from A to B. So the tip of the arrow or the vector is at B, and the start or the tail, the back of it, is at A. So one of the ways we can do this, right, is we look at this and we go, okay, it's to get what delta x is just from the ordered pairs. I can look here and I can say x goes from 16 to 10. Is that a negative or a positive? From 16 to 10. That's negative 6. And the alternative is that I could have done 10 minus 16, right? End minus start. The other thing I have is that y goes from 2 to 5. That's a positive. How much does it grow by? It grows by 3. Now, instead of calling vectors, naming them with the tail and tip, we can use a single letter, and it's usually a lowercase letter. So when you use the tail and the tip, you use capitals like AB, it means from A to B, but you can also use small letters, lowercase, and the most common ones are U, V, W for vectors, sometimes A and B, but in this case, so we can, what I said here is, okay, you know what, we're going to call AB U. So you can just get used to different ways of naming them. And so U would also, of course, be negative 6 and 3. And if I want to think about this, okay, what does this vector look like? Delta x is negative 6, so it's 6 this way, and then it's 3 up, and then that's the vector right there. Okay, so it's negative 6 and plus 3, and that would be vector u there. And then we'd have to have a tip on that. So remember that this can be a vector by itself, delta x, and delta y can also be a vector on its own. This is vector u here. Okay, so that's A. So for B, one of the ways we characterize a vector is its length, or what we call its magnitude, right? And the magnitude could be a velocity vector, and the velocity is 80 kilometers an hour. So you have some sort of scale. 1 centimeter is 10 kilometers per hour. So 8 centimeters would be 80 kilometers an hour, right? So it's a magnitude or length. It's a lot easier when you talk about a translation because you can just think of it in terms of centimeters, say. So first thing we're going to do is we're going to come up with a length. So I've got this right here. To get the length, you can imagine, right, that it's just Pythagorean theorem. So for this one here, I'll just draw a little picture of it right here. We know that it goes 6 this way, right? Then it goes up by 3, and that's our vector there, right? That's our vector there. So that's AB right here. So delta x is negative 6, and delta y is 3. Okay, delta y is 3. So what do? Well, we take this and we do Pythagorean theorem, right? We do the Pythagorean theorem because the vector AB is the length of the hypotenuse. Okay, here's our formula. It's just Pythagorean theorem. That's all it is. So vector AB, these bars are, as you know, absolute value, right? So the length of a vector is only positive. You can't have a negative length of something. So AB represents, with bar around it, represents length or magnitude. And by Pythagorean theorem, since it's the hypotenuse, it's just the square root of delta x squared plus delta y squared. So in our case, we know delta x squared is negative 6, or delta x is negative 6, so that's squared, plus delta y squared. Well, what's delta y? Delta y is 3. That's 3 squared. What does that work out to? And let's just erase that. And that equals 6 squared is 36, and 3 squared is 9. 36 plus 3, or 36 plus 9 is 45. That's the square root of 45, okay? And that is what we call the magnitude or length of vector AB. Now, we can write this as a decimal if we want. So that is 6.71, okay, if I use my calculator. All right, so that's the length. The next thing we want to look at is what's called the polar representation of a vector. And that's where we use radius and angle in standard position to describe the vector. So right here, this thing here. So instead of x and y, we use r and theta. And you're going to see how this works. So it's pretty neat, actually, this whole polar form. I don't spend much time on it. This will probably be the only time we do it, but I do want you to see what polar form is. So when we do this, I'm just going to take you through how you would go about this. So what you do is you always put, if you want to get the angle's measured, by the way, from 0 degrees, right? So it's an angle in standard position. And your vector, the vector forms like the ray of the angle, right? So that's like the terminal arm of the angle. And again, theta is always measured from 0 degrees, or of course that's also 360. R we know is the related angle or related acute angle. That's the angle between the closest x-axis. Okay, and the vector. R is closest x-axis. So there's a reason why that's important, because, but again, so what I want to remind you of is what you do is you always put an origin at the tail of the vector, okay, at the tail. So a little crosshairs there. And what that's going to do for you is allow you to figure out that angle, all right? And so our scenario is this. We know that this measurement here is 3, right? That's delta y. We know this measurement is 6, but what we're going to do is we're just going to do absolute values for those, delta y and delta x. This right here is 6, okay? And then what I'm going to do is this angle here is r, the related angle. So it's this little angle here. So r is always going to be, it's actually quite a simple calculation. Every single time, r will be delta y, absolute value, over delta x, absolute value, okay? Every single time. It's that formula there, folks. That's your related angle, the angle between the closest x-axis and the vector. So in this case, what is r? R is going to be delta y, which is absolute value of delta y, which is 3. Absolute value of delta x is 6. Okay, so that's you're going to do that calculation. What is tan inverse of 3/6 or 1/2? So the tan inverse of that is 26.6 degrees. Okay, so that little angle there is 26.6. So now what we do is we draw another picture and we make sure that we can understand what our angle should be. Okay, again, I have the xy coordinate origin at the tail of the vector, okay? And then the r we know to be, the r is given as 26.6, right? I'll just draw that in here, equals 26.6. And what do we know about these two angles? Well, they have to add up to 180. So what will theta be? Theta is the principal angle, right? Starting from 0, rotating counterclockwise. 180 minus 26.6. Well, 180 minus 30 is 150. So the angle's a little bit more than 150. It's actually 153.4. So one of the ways that we can describe our vector then is this. So vector AB in this form is r comma theta. R represents the radius, which is the length or the magnitude. Do you remember what that was? 6.71. So think of it as being 6.71 centimeters long is the length of that vector. And then what's the angle from 0? The angle from 0 is 153.4 degrees. Okay, that's just a whole other way of describing that vector. Okay, that's called polar form. And you can imagine that that one's kind of useful for trigonometry because you have an angle in degrees, right? And you have a length. So instead of having delta x and delta y, it's just a little bit different. So let's take a look at what that really means. So I'm going to zoom in here, and we're going to take a look at this. So if I have a vector like so, okay, I have a vector like that, this right here. So there was two ways to describe this. One way to describe this was that delta x and delta y were, what were they? Well, I can put that underneath there. Delta x and delta y were -6, 3, right? That's one way to describe that. That's a vector. So that means that I have 2, go left by 6, and then go up 3, right? So that's one way to describe this vector. And what kind of instructions that's giving us is, how do I go across the x and y axis that are perpendicular to each other to go from the tail or start of the vector to the tip or the end of the vector? Go left 6, up 3. That's one way to get from the start to the end of the vector. There's a whole other way to do it, right? There's a whole other way to do it, and that's with what's called polar form. Polar form is r, theta. So in this case, what you would want to do really is do theta first, right? You'd want to do theta first, and theta was 156.6 degrees. Oh, sorry, 153.6 degrees. Whoa, Mr. Long. 153.4 degrees. Okay, 153.4 degrees. So I go to this little crosshair, and then how would I draw this vector? Well, I'd have to go 153.4 degrees from 0. And then what would I do? I would make that vector 6.7 centimeters long. Okay, and then that would be my vector. So you can see there's two totally different ways to get that vector, to be able to draw it to scale or accurately, to measure it. They're equivalent but totally different ways. Okay, this right here is called polar. This right here is called Cartesian or algebraic. Okay, and then the third way to do it is just to draw a picture. That's geometric. Okay, so 3 ways to represent that vector. So what I'm going to do now is just stop this video and then finish up the other parts with the last video.